So far, we've been conducting heat transfer problems along a rectangular slab, where the Cartesian coordinates of x, y, z made the most sense as the geometry and the coordinate system for our problem. But in a lot of problems in science and engineering, we deal with other types of shapes and geometries. For example, a cylinder. Suppose that we have a solid piece of cylinder of some length L and radius R0. We like to measure the heat transfer in this problem subjected to the following boundary conditions. Just like that. So the lateral surface around the cylinder, so the wrapper around the lateral end, is fixed at 0 temperature and in some ice bath. So I just put 0C here. You could use deviation variables so that it's 0 temperature. The Celsius, Kelvin, don't worry about so much about that detail. Let's suppose I have a 0 Dirichlet boundary condition along the lateral surface. I have a 0 boundary condition also along the left-hand boundary at this position here. And then on the right-hand edge of this cylindrical piece of material, right-hand side is subjected to boiling water, so 100C. Okay? Those are our boundary conditions. So for a rectangular slab, we had boundary conditions at the left, the right, the top, and the bottom. In the cylindrical geometry, we have boundary conditions on the ends, just like we did before. But now the boundary condition sweeps along the entire surrounding direction in angular space. So all around the lateral dimension, it is subjected to 0 temperature. Now, when you think about trying to solve the temperature profile in a problem like this, whether it's steady state temperature profile or the transient profile, you would immediately think that this might turn into a three-dimensional problem of x, y, and z. In general, if you tried to use Cartesian coordinates, it would turn into a weird three-dimensional problem because at every point, it might vary as a function of x, y, z along this material. So then Cartesian coordinates in this particular geometry clearly isn't the right coordinate system that we should be using. For a cylindrical geometry, we should be considering the use of cylindrical coordinate system. So not x, y, and z, but instead r, the radial position from the origin, right there, pointing radially outward, a axial dimension z that points axially along the cylinder, and the final coordinate of angle, of theta, that wraps around the cylindrical lateral direction. So in general, x, y, and z would be replaced with the cylindrical coordinate system of r, theta, and z. So in general, the problem would be a three-dimensional problem of r, theta, and z, because at every point you have some r direction, dimension, theta, the angle that points to a particular angle along your cylinder, and then how deep you are axially along the cylinder. But for this particular problem, because the lateral surface is subjected to a uniform temperature that is fixed at 0, or just a constant temperature in general along the lateral direction, we wouldn't anticipate any variations in temperature along the theta direction. Meaning, if I were to go to some point here and measure the temperature at that particular radius, z position, and theta position, and just change the theta to go to the other side of the cylinder, right at that point, where the radial distance from the origin is still the same, and the z position along the axial direction is still the same, but I've only changed the theta direction. Then I would anticipate the temperature to be the same at these 2 points because it is what's called axisymmetric. It's 0 temperature all the way around. It's 100 here, 0 here. I wouldn't expect there to be any variation in temperature along the theta direction. Therefore, this problem should not depend on the angular coordinate theta. This is called the axisymmetric approximation or assumption. This is an assumption that we're making about the problem, that it does not depend on the angle, or theta. So it is rotationally symmetric about the axis z. So then all we need to solve is actually a 2D problem of r, where we are, how along the angular space from the core of the cylinder to the exterior surface, that's the radial distance, and z, how far we are along the axial direction along the cylinder. Those are the two spatial coordinates, just like how we solved x and y. X and y has now been replaced with r and z using the cylindrical coordinate system. And time is the same time. We haven't made any distinction between the two, depending on the different geometries. And in fact, many problems in science and engineering, this axisymmetry or rotationally symmetric approximation ends up working extremely well. So a lot of these problems, we just end up making this axisymmetry assumption. So we like to solve the heat transfer problem inside this solid piece of cylinder. Now, the governing equations do not change irrespective of what coordinate system you are using. So let's first write down the heat equation. This is our favorite equation for the last couple of weeks, the heat equation. This form does not change. Where it does change, depending on the coordinate system, is the precise form of this Laplacian operator. So in rectangular coordinates, the Laplacian operator is just simply the second partial derivatives of x, y, and z that acts on the scalar variable temperature. For cylindrical coordinate system, the Laplacian operator looks like the following. Just like that. So there's still three terms coming from the three directions, r, theta, and z, but the precise form of the second derivative changes just slightly. First, the z direction just looks like the rectangular coordinates for x, y, and z. That doesn't change. The theta direction has just a factor of 1 over r squared coming from the Jacobian of a cylindrical wedge that you need to put in there. And lastly, the r direction has a factor of r in there and 1 over r outside in front. It still overall is a second derivative form, but you need to put in some Jacobians here and there. Similar to how when you take an integral in cylindrical coordinates, you need that r dr d theta. The origin of these r's being thrown in there here and there is the same reason. It's just the cylindrical coordinate wedge that you create. There's a factor of r as you go further and further in space because the area in the perimeter gets larger and larger as you get further away from the origin. Now, like I said up here, the axisymmetry approximation ends up working very well. And for this system, we would expect it to be axisymmetric, meaning it should not depend on the angle theta. So for this particular problem, the temperature should not vary as a function of theta, and so this middle term will be 0. And this is a result of axisymmetry. Now, we would like to solve this heat equation where we have the transient left-hand side and this Laplacian in r and z on the right-hand side. Now, just like how we solved the rectangular coordinate system, where we separated the steady-state solution from the transient solution, let's do the same thing here and focus on the transient part later and only focus on the steady-state solution for now. So we would like to get the steady-state solution of this material. I have a solid cylinder, 0 temperature on the left, 100 degrees on the right, 0 all the way along the wrapper. What does the steady-state temperature profile look like in that case? Let's write down the boundary conditions that have to be satisfied for us to obtain a solution to the steady-state solution. Our equations at steady state, where the temperature profile depends only on r and z, looks like the following. This line right here on top is simply taking this r second derivative. Using the product rule, you get that. Okay, the way you could see it is you take the product rule first of this first partial derivative of r, partial t, partial r. You get 2 terms out of that when you use the product rule. The second derivative is going to have an r that will cancel the 1 over r outside. You just get partial squared t, partial r squared. The second term is the other part of the product rule. And lastly, the z derivative just comes straight down. So this is the steady state temperature governing equation for the heat transfer. Now, the boundary conditions. First, at r equal to r naught, which is along the lateral wrapper of the cylinder, it's equal to 0 temperature all the way around. Now, the second boundary condition is a little bit weird. Usually you would have in rectangular coordinates a boundary condition at y equal to 0 and x equal to 0, right? The bottom part of the rectangular slab had some temperature. The left-hand part of the slab at x equal to 0 also had some temperature. In this case, the bottom corresponds to r equal to 0, which is right at the origin. So that would correspond to all the points that fall along the center core, the midpoint, the origin, the line that goes all the way across, sitting at the center of this cylinder. What is the temperature at that point? Let's return to that a little bit later. So I put a question mark there for now. Let's move on. Boundary condition number 3, which says that the left-hand surface at z equal to 0, it's set to an ice bath at 0 temperature, and on the right-hand side at z equal to L, it's set to a boiling hot water bath at a temperature of 100. So this is the governing equation and 4 boundary conditions that we like to solve. This is a well-posed boundary value problem. Now, let's think about how we might solve this problem. So what we did before with all of our problems so far is to try separation of variables. Is exactly what we're going to do here as well. But when you take a step back and look at these equations, it looks kind of similar to what we've been solving. So if you were to take away the second term in the governing equation, this middle term, 1 over r partial t partial r, without this term, it would just be your ordinary heat equation that you've been solving in rectangular coordinates, r and z, x and y. This presence of this middle term is actually the term that gives rise to curvature. So this second term is a correction to rectangular coordinates that gives curvature of the cylinder along the r direction. So even with that term, we should still charge ahead with trying separation of variables and separate the r dimension with the z dimension, just like we have always been doing with separation of variables. So in separation of variables, we're just going to write the full temperature profile as a product of a function only of little r, so capital R times capital Z, which is only a function of the lateral direction little z. We're going to take this solution, which we've assumed, plug it in to this PDE, and let's see what we get out. So this is just direct substitution of this temperature profile directly into the partial differential equation. Of course, for the first 2 terms, the capital Z function can take outside of the r derivative because it's only a function of z. This last term is not a function of r, therefore the capital R can come outside. Now, all we're going to do is divide every term by capital Z and capital R and put all the r's onto one side of the equation, all the z's onto the other side of the equation. We get something that looks like this. Again, a familiar sequence of steps that we've been taking in rectangular coordinates, except there's this extra term here that accounts for curvature. But the same line of argument still applies here. On the left-hand side, everything here is only a function of the independent variable r. It only depends on little r. Everything on the right only depends on z. Therefore, the only way that this could ever be true is if they are both equal to a constant. Same argument. And we're going to call that argument and the constant on the right-hand side negative mu squared. You're going to see why we've called it negative here. For the same reason that we chose a negative sign for the rectangular coordinate geometry. We have 0 boundary conditions, homogeneous boundary conditions along the r direction. Therefore, we want our orthogonal eigenfunctions and orthogonal basis functions, like basically sines and cosines, but the cylindrical coordinate version of that, to fall along the r direction. Along the z direction, because we have a non-homogeneous boundary condition, especially along the right-hand side, we want to reserve the other function, in this case the r direction, to have the orthogonal basis functions. Along z, we'll just let whatever it needs to be. All right, so if that didn't make any sense to you, we're going to come back to that a little bit later. But the most important part is that at this point, we have two separate ODEs to solve. One ODE for capital R, one ODE for capital Z, just like we've always been doing. So let's solve those two separate ODEs. First, the easier one. The z-directional ODE is simply these two terms on the right-hand side set equal to each other. You find your characteristic equation. You're going to get real, distinct roots. And therefore, your solution along the z direction is simply exponentials, one positive, one negative root. Easy. Your simple, constant coefficient, linear, second-order ODE. No big deal. Now, let's try to figure out the other ODE here, which seems to be a little bit more challenging. All right, this is the other ODE that comes out of separation of variables. All I've done here is to multiply this entire equation across by r squared and capital R. Therefore, the first term, the second derivative, just acquires a little r squared. That's the radial coordinate, that's the independent variable emanating from the origin outward to the lateral surface. The second term has the 1 over capital R cancel. 1 over r just becomes positive r, upstairs linear r. First derivative of the radial position. And lastly, I've brought over the mu onto the left-hand side, and we just get mu squared, r squared, and capital R. The whole thing is equal to 0. And you stare at this equation, and you keep staring at it, and you recognize that it looks something familiar to what we did earlier in the course. Earlier in the course, you guys might have forgotten, but there was an equation that looked something like this. This equation, I'm sure you've seen it before, you probably just forgot because it's been so much time, is a second-order ODE, but it's a special type of ODE. It's called the Bessel's ordinary differential equation. And you get, as solutions, Bessel's functions. So let's see if this equation can be mapped to this top equation. And the similarity is very clear. If lambda were to be equal to 0, then it looks more similar already. The only difference is that now we have a mu sitting out in front here, whereas we just have an x right there. So we can do a quick substitution and see if we can make a mapping between these two equations. So if we let lambda equal to 0 and make the substitution, x is equal to mu times r, then you can actually show a direct mapping. For example, this second derivative, y double prime, is d squared y divided by dx squared. If we converted variables from x over to r, we're going to get a factor of mu that pops outside when you substitute x for r. Then this x squared term out in front will also carry a mu squared, and those two mu squared terms will exactly cancel. Same thing for the second term. X will now become mu times r. This dy dx will now become dy d little r with a mu that pops outside that will cancel this mu on top. And lastly, this x squared will exactly map onto this term. And when lambda is equal to 0, this term goes away. And now the two equations become identical. We know what the solution to this Bessel's ODE looks like. They're Bessel's functions. Just like that. So the function capital R is going to equal some constant of integration a times j sub lambda, which in this case is just simply equal to 0 because lambda is equal to 0. Before we introduced it, we said j sub n, y sub n. where n was this value here, or y, or I think I said j sub lambda, y sub lambda, and then depending on the value of lambda, you get different types of Bessel's function. But in this particular case, lambda is 0, so we have j sub 0 and y sub 0, and two constants of integration a and b. So these are the Bessel's function of the first and second kind. And here are your solutions. And I don't want you to be afraid of Bessel's functions. It looks spooky because it's got j's and zeros and y's, but when you think about it, sine and cosine, which is what you got here normally, right? You got exponentials on one side, separation of variables give you sines and cosines on this problem. Sines and cosines are also weird functions. You already have known about sines and cosines from a long time ago when you first took geometry, so you kind of have a sense of what sines and cosines are like. But if you just told someone sin or cos, what are you talking about? It's just a mysterious combination of letters that has a mathematical meaning, now you know from the power series. But in general, it's just a combination of letters and symbols that represents a mathematical function, an actual power series. It's the same thing here. J0, Y0 is just a power series, a bunch of numbers added together, just like sines and cosines. So it's a series solution represented conveniently and compactly by using J's and Y's. That's all. So you shouldn't be afraid of these things at all. You should be afraid of them to the same extent that you should be afraid of sines and cosines. One, you have familiarity, one you don't. That's the only difference. So at this stage, we have a solution for the R ODE and solution for the Z ODE, and you just combine them together. So here is the full solution as we have it so far. Coming from the separation of variables, we have two solutions, capital R and capital Z, that we've plugged in here. Just like how we did it for rectangular coordinates, sines and cosines with exponentials on the other side, or sinches and coches on the other end. Identical. Just replacing sines and cosines with the Bessel's function of the first and second kind. That's it. Now, at this point, what we did before was to start applying boundary conditions. We do the same thing here. Now, usually when we start applying boundary conditions, think about which boundary condition did we apply first. Usually we applied the boundary condition at x equal to 0 or y equal to 0 because that helped us make a lot of progress on determining one of the boundary conditions. In this particular case, x equal to 0 would correspond to the radial coordinate being 0. And that's the boundary condition where we're not really sure. That's that boundary condition right there. So let's recall, before thinking about this boundary condition a little bit more carefully, what these Bessel function solutions look like. What does a function actually look like as we vary little r? So the Bessel's function, J0, looks something like this. As a function of r, it has a finite value at r equal to 0. So at that point, it achieves some finite value, and it oscillates back and forth, back and forth. Remember that puddle picture that I showed you? It just like ripples in a quiescent lake, just ripples. Just goes up and down, up and down, up and down. Okay? But the key point is it is finite at r equal to 0. At the origin, this value is equal to a finite number, just a number. Now, the other Bessel's function looks like the following. It looks something like this. Now, it also oscillates back and forth, just like sines and cosines oscillate back and forth. But the key point is that at the origin, this function y naught diverges to negative infinity. Okay? So it goes all the way to negative infinity as the radial coordinate gets closer and closer to the origin. So let's think about it. That would be like, we're trying to solve this heat transfer problem. And as we go closer and closer to the origin, from the lateral edge closer and closer to the origin, the temperature is diverging to negative infinity. That just wouldn't make sense. Because if the temperature profile here, this y0 function, diverged to negative infinity, that would be terrible. I mean, that just would be aphysical. You would never have a negative infinity at any point along this continuum space of this material. Therefore, we better kill off this term by setting b is equal to 0. That's just based on a physical argument. The temperature cannot be negative infinity. This function that we've included does go to negative infinity, and therefore we must kill it off by setting b equal to 0. So we've used one of the boundary conditions in an interesting way to discover that the constant of integration b must be equal to 0. So now, returning to this mystery boundary condition that we've kind of untouched for now, we can make that more precise. So the temperature profile, as r goes to 0, must be a finite value. This boundary condition is a very common boundary condition that we apply for cylindrical coordinate system and spherical coordinate system, with the radial direction that emanates from some origin outward. Because when you go down and shrink to the point of 0, you have to flip back onto the other end. So that would be kind of like going from the North Pole, coming down, 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 crossing the z-axis, and then now going towards the South Pole. Now, at that crossing point, the temperature has to be finite. It can't blow up to some nonsensical negative infinity or positive infinity. Another way to pose this boundary condition is what's called a symmetry boundary condition. It's saying that as I go from the North Pole to the South Pole and cross the origin, the derivative must be equal to 0, meaning that it must be symmetric without a weird kink happening at the origin. So sometimes you'll see this boundary condition written as the derivative of the temperature at r equal to 0 at the origin must be equal to 0. And people will often call that a symmetry boundary condition. And you can easily see that. If the temperature were finite, and if you were to take the derivative as a function of r as you cross r equal to 0, this would be equal to 0 because you take the derivative of both sides, a finite number, it's a constant, the derivative of that is equal to 0. So a lot of times the second boundary condition here is often called a symmetry boundary condition. But either way, it's grounded in a physical argument that whether it's symmetry or whether it's temperature has to be finite, we're able to use one of the boundary conditions to get rid of this b equal to 0. Just like how we did it with rectangular coordinate system. Just a subtle difference in how we write down the boundary condition at r equal to 0. Okay, so now we have only one Bessel's function, J0, left over. And we like to use boundary condition number 1 to figure out more about this term right here, and specifically about the eigenvalue. Again, remember rectangular coordinates. One of the boundary condition 2, at x equal to 0, removed one of the terms. The sines or cosines died. One of them got away. You had the other one left over. You use the boundary condition at the other end at x equal to L. In this case, r equal to r naught. That should give you the eigenvalues, because if a were equal to 0, that would just give you the trivial solution. So the only non-trivial way to satisfy this boundary condition is if J0 of mu times r naught were equal to 0. Let's write that down. So I've just written here boundary condition 1, which says that little r equal to r0, which is along the lateral surface, the temperature is equal to the 0. Therefore, we take the solution that we have. Again, now b is gone. We just have a j naught mu times r naught times all the dependencies on z. That must be equal to 0. The only way we can make this true for all z is you have to remove this term somehow. So either a is equal to 0 or j naught of the argument mu times r naught must be equal to 0. If a were equal to 0, you get the trivial solution. Therefore, we need to make this Bessel's function of the argument mu r0 to be 0. So clearly, this j naught of the argument mu r naught must be equal to 0. And remember that for rectangular coordinates, you got something that looked like this before, where sine of the argument lambda, or in this case we're calling it mu, times the boundary at capital L, that must be equal to 0, and therefore mu times L were equal to n pi. And n took on integer values. So these were all the points of mu, we called it lambda before, where it crosses the 0. Sine crosses 0 every n pi cycles, and we had discrete values of the eigenvalues. Now, for this case, very similar. For sine, it crossed the boundary every n pi cycles. For this function right here, j naught as a function of r starts at some finite value, goes down, up, down, up, down, up, and it does go to 0. It does cross the origin. It crosses here, 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 and so on. So there is an infinite number of zeros that the Bessel's function could equal. Just like how sine crosses 0 every n pi cycle. This also crosses 0 an infinite number of times. But there are some differences. The first difference is that the 0 spacing is not the same. Here, for sine, the spacing was always equal to pi. So at pi, 2 pi, 3 pi, 4 pi, so at every pi cycle, the sine was equal to 0. So they were evenly spaced. The zeros were evenly spaced. For the Bessel's function, the zeros are not evenly spaced. So the distance between the first 0 and the second 0, and the second 0 to the third 0 to the fourth 0, the distance between each 0 is not the same. That's one difference. Secondly, we can't calculate the zeros conveniently with pen and paper analytically. With sines and cosines, you can write it down. We wrote it down here. Mu sub n is equal to n pi over L. We can write that down on a pen and paper. For the Bessel's function, we need to calculate the zeros numerically. So there is a power series that tells you what that function looks like. You just have to find the zero coefficients. You basically have to do F0 on MATLAB to find the zeros of this weird function and look for where it crosses the intercept, to look for the zeros. And a lot of times people will write the notation just for convenience that we have to, of course, find these roots numerically, but we will define some lowercase jn as the nth zero of this function. So give me an index n, that's the nth root of the 0. So for example, j sub 3 is 1, 2, 3. That root right there, this distance, would be equal to j sub n. So it tells you which root number that you obtain, again, obtain numerically. It's just the bookkeeping, find out which root that you're looking for. So with that definition of jn telling you the root number of this function, we can obtain our eigenvalues mu sub n, which is simply equal to jn divided by r naught. Again, in analogy with sines and cosines, let's draw a little cartoon to show the similarities. So here I've drawn a sine wave, and we found the roots of sine x being 0, which is how we obtain the roots of the boundary condition up there for rectangular coordinate. The roots were just evenly spaced as n pi. All these zeros, everything here, each of those spacing was n pi apart. The only difference with jn, the roots of the Bessel's function, they're not evenly spaced, just like how sine is evenly spaced, and you have to find them numerically. But that's the only detail. Otherwise, it's the same. You just get an infinite number of roots, just like you get an infinite number of roots for sines and cosines. Now let's clean this up, and we'll continue with where we are in the problem. Okay, so here's our solution as of now. We know what the mu's now are, but we need to apply boundary conditions along the z direction to do something about c and d. Now, boundary condition number 3 is pretty easy. Let's just quickly do that so we can get a relationship between c and d. Just like that. So all we have to do is evaluate z is equal to 0, and out comes the following. Just like that, z equal to 0 removes both of the exponentials because they're just 1. And so you get c plus d in the bracket times the Bessel's function for arbitrary positions of r must all be equal to 0. Now, the only way to make this true for all possible values of mu and r is if c and d were equal to the opposite. So if this was equal to 0. So c is equal to negative d. OK? So no big deal. That just gives us a relationship between c and d. And remember when we used cinches and coches instead of exponentials when we did the 2D heat transfer in x and y? We could have totally done that here. I just chose exponentials in this case. And previously, I said you can also use exponentials for the x and y case. They're the same. Using cinches and coches here would have also been convenient now in hindsight, because at z equal to 0, the cinch term would have died and the cosh would have stayed. Right? So we're just kind of finding that out, right? Because now when you make c equal to negative d, you'll get a cinch that comes out anyway. Okay, so the result is the same. So I'm just going to swap c is equal to negative d, pull the d outside. So you get this. The negative sign just shows up in front of this negative exponential, and the d just factored right outside. So like I said, this term right here is a cinch. It would just be this divided by 2, but it's just linear combinations of taking exponentials. Now, we have an a in the front, d in the front, which are both constants. Let's just combine them into another common constant. Just like that. So I've just called the product of those two constants, a and d, equal to a new constant e, which we've also done for rectangular coordinates. So you can probably tell me at this point that we're doing the same thing. Morally, the different coordinate systems is no big deal. Sure, the details of the curvature term giving rise to a Bessel's function instead of a sine and cosine, that's the only difference. But otherwise, the overall procedure is the same. One of the zero boundary conditions gives you one of the constants of integration, makes your problem easier. The other boundary condition at r equal to capital or r equal to r naught gives you the eigenvalues. Same thing, the same procedure. All right, so now I'm going to remove this boundary condition because we're done with using that. And we also know at this stage that using the boundary condition at r equal to r naught gave us the eigenvalues for mu n. And therefore, again, we have an infinite number of possible solutions that satisfy the governing equation and obey boundary conditions 1, 2, and 3. So we use superposition to add up all the solutions. So boundary condition 1 gave us an infinite number of eigenvalues mu sub n, which is equal to j sub n, which are the roots of the Bessel's function j0. So j0 of the argument j sub n is equal to 0. Those are the points where this Bessel's function crosses 0. We have infinite many of those. They're not evenly spaced like sines and cosines, but we have infinitely many number of zeros, roots. So that suggests that we should use superposition to add up all of those independent solutions together to obtain this solution right here as the sum of 1 all the way to infinity of this solution. And now we have one constant of integration e sub n that we need to find. And we should use our last boundary condition at z equal to L to obtain our constant of integration. So I've just applied boundary condition number 4, which says that the temperature at z at L is equal to 100, the right-hand side. What I've done here is to bring this exponential term in brackets in front because you can see that everything here is just a constant. It's just a number that depends on the index n, right? Because exponential of mu sub n are just zeros of this rapidly oscillating Bessel's function. Those are just numbers, specific points at which they're equal to 0, just a constant. Therefore, this whole thing could be lumped together into a single constant, just like that. And we did something similar for the 2D xy Cartesian coordinate problem as well. We lumped together the terms and just called it a single constant and did a Fourier series from that. So this also looks kind of familiar to you because it was summation of 1 to infinity of some coefficient times an orthogonal basis function is equal to a function, in this case, a constant function of 100. So previously, this function was equal to a sine and cosine. You knew exactly what you needed to do. When this were a sine eigenvalue times x, you use the Fourier series. You multiply both sides by sine m pi x over L. You use orthogonality. You picked out each unique coefficient fn that satisfied this right-hand side. Now, Bessel's function, just like sines and cosines, are orthogonal eigenfunctions or orthogonal basis functions. So you could use orthogonality to obtain the coefficients f sub n, just the same way we obtain coefficients for sines and cosines. So Bessel's functions are orthogonal functions. There's a property that says if you integrate from 0 to r0 of the product of two Bessel's function, j sub I, so of arbitrary order, of two different indices n and m, integrated over the Jacobian r times dr. Again, you need the Jacobian because you're using cylindrical coordinate systems. You need a factor of r right there for the Jacobian. You take the area under the curve, just like sine and cosine, or sine n pi x, sine m pi x. Same thing. Orthogonality tells us that this integral is equal to 0 if n and m are not the same. And it's equal to this thing, a constant, r0 squared divided by 2, Bessel's function I plus 1, so it gets promoted by 1. So in this case, we have a j0 that's going to be promoted to a j1, evaluated at mu n r0, when the index n and m are the same. When they're the same, you get a non-zero number. When they are the same, you get 0. This is the definition of orthogonality, which was also true for sines and cosines. When it was sine times sine, it was 0 when n and m were not the same, and it was equal to L when they were the same. That's the only difference. But otherwise, the property of orthogonality just still goes straight through. So all we need to do is to take this equation, multiply both sides by j0 mu m r, both sides, integrate from 0 to r0, and what we'll find is that every term inside the summation is going to be identically equal to 0, except when n and m are the same, and we can pick out uniquely the value of the coefficient f sub n for that value, and build up all of our weights and our coefficients by varying the value of n. Identical to the normal Fourier sine and cosine series. Okay, let's write this down. All right, so at the end of this long, beastly calculation, we're all done. So again, I've circled the final solutions in pink up here. This is your full solution. Again, the temperature profile is a function of little r and little z. I feel like I'm doing a recap again. I'm the one doing it, I'm getting lost. I'm sure you're watching this and you're also getting lost. So temperature is a function of the radial coordinate r, axial coordinate z. It's a function of this Bessel's function j0, which has an argument of the eigenvalues mu n. Mu n are the roots of the Bessel's j0 that goes back and forth, that you obtain numerically. So there's an entire table of little j sub n that gives you the zeros of 1, 2, 3, 4, 5, all the way down of all the roots of this function. So mu sub n are just numbers. The other argument here is the little r, the radial vector, or the radial coordinate. That's going to have the r dependence multiplied against the z dependence, which are just exponentials. Now, the coefficients e sub n, we used orthogonality to obtain. That's down here. E sub n is equal to fn divided by this factor right here. I ran out of room, so I just multiplied it inverse. So this should be on the bottom. The fn we obtained using orthogonality, using the definition and the orthogonality of the Bessel's function. So here you have it. And like I said, morally, it's the same as rectangular coordinates and sines and cosines. The only difference is the Bessel's function and the roots being now numerically obtained. I wanted to make one last comment about cylindrical coordinate systems and what we've done here, and then we're all done. Let's do that brief aside. So you just saw an example for the first time where we actually developed the Fourier series not in sines and cosines, but in Bessel's functions. It turns out that there is a thing called a Fourier-Bessel series. And all along, we were just doing a Fourier sine and cosine series. We called it just Fourier series, but in general, there is a Fourier series of lots of different orthogonal basis functions. It just so happens that sines and cosines are the most commonly used ones, but there are lots of other ones like a Fourier-Bessel series. All we have to do is express a function using a sum of a bunch of Bessel's functions, j lambda and y lambda, just like sines and cosines. Just like sines and cosines. You're familiar with this because we've already done this many times. And sine n pi x over L, n pi over L are generally the eigenvalues. Up here, we have to obtain them numerically. That's one difference. The other difference is that sine has zeros every n pi cycles. Up here, Bessel's functions don't have zeros in evenly spaced values, right? Evenly spaced with pi, like they are with sines. That's the only difference. But otherwise, you can express any arbitrary function, just like you could do for sines and cosines, using Bessel's functions. OK, so now I wanted to return to one point during the separation of variables, very, very early on, when we took the temperature profile and we split it into an r and a z, and we set the sign as negative mu squared. We had a point pretty early on in the derivation where we said, OK, we have some function of r only on the left-hand side, some function of z only on the right-hand side. And we said, therefore, it must be equal to a constant. And that constant must be some number, which we called negative mu squared. Now, the sign of that right-hand side was chosen strategically so that this ODE in R produces the right sign for the Bessel's equation such that we got j and y as the solutions. Now, if you chose the wrong sign here, if you chose positive mu squared, you would have gotten the modified Bessel's function, which are not j and y, and which are not orthogonal functions. That will be analogous to Sinches and Koches, or exponentials in rectangular coordinate space. So there are an exact analogy of rectangular coordinate space with cylindrical coordinate space. You just have to make the translation away from sines and cosines, exponentials, over to the Bessel's function, the modified Bessel's functions. To demonstrate that a little bit more concretely, I've put the two different cases. The correct case, where you put a negative sign out here, makes a positive sign right here. That produces the solutions j0 and y0, which are called Bessel's functions. And the characteristic about them is that they are orthogonal. And the functions oscillate. One diverges, the y0 diverges to negative infinity at 0, but the key point is that they're similar to sines and cosines. Right? Sines and cosines are orthogonal, they oscillate, and it's the case where there's plus on the left-hand side. Now, the opposite, if you were to come here and make this a positive sign, then when you split the variables and solve your RODE, you would have a negative sign here, which actually completely changes the solution. Just like how it did with exponentials in Sinches and Cauchys. Completely changed with one sign difference. These solutions, K0 and I0, I know, couldn't they have been more creative with naming? Or you're just like overwhelmed with all these symbols. These are called modified Bessel's functions. Modified Bessel's functions of the first and second kind. And these functions do not oscillate. They look just like exponentials, actually. And they're not orthogonal. That's the key point. And because they're not orthogonal, you cannot form a Fourier series using K's and I's. You can only form Fourier-Bessel series using J's and Y's or the Bessel's function. Just like sines and cosines. You can form Fourier series using sines and cosines, but you can't form Fourier series using exponentials or Sinches and Cauchys. All right, that's all I wanted to say about cylindrical heat transfer. At the beginning of next lecture, I'll do a very brief recap of the transient heat transfer problem in different geometries and how to tackle the transient part. But overall, at this stage, you know everything you need to know about solving transient heat transfer, and you've seen this case for the cylindrical geometry, so the particular geometry and the shape of the heat transfer problem you want to solve should not deter you. That should not be a hindrance to whether you can solve or not solve that problem. Details are different, but morally, the concepts of the approach are identical regardless of the geometry. All right, I will see you guys next time. Bye!